this learning unit, we will discuss on the pericyclic reaction. Okay, in organic compounds or reaction of organic compounds, there are three common reactions that usually involve organic compounds. The first one is the polar reaction. So in polar reaction, we normally have nucleophile and electrophile, and then it will give us desired products. In another reaction, which is called radical reaction, it involves radical, and this reaction usually occur when you have alkane. And the third reaction is pericyclic reaction, which is a reaction that occurs as a result of organizing the electrons in the reactants. Okay, this is the principle of pericyclic reaction. So, in pericyclic reaction, there are simultaneous bond-making breaking process with a cyclic transition state involving delocalized electrons. And then the combination of these steps is called a concerted process, where normally intermediates are skipped. In pericyclic reaction, we normally involve conservation of orbital symmetry theory, where we use lots of molecular orbital theory in defining pericyclic reaction. So there are three components of pericyclic reaction. The first is the structure and configuration of the reactants, whether the reactants is cis or trans. And then we have a condition of the reaction, either the reaction is done photochemically or thermally. And then the structure of the reactant plus the condition of the reaction will influence the configuration of the end product, meaning the product is highly dependent on the condition and also the configuration of the reactants. In pericyclic reaction, we are focusing more on the molecular orbital. Okay, in this slide, we can see that this is a molecular orbital of ethylene. So you know that ethylene is 2 carbon with a double bond. Okay, in this case, why we have p orbital is because we have pi bond. Pi bond here. So in this case, we have two bonds here. So if we have two bonds, meaning we have 2p orbital. So you are familiar with the drawing of molecular orbital diagram. So in molecular orbital diagram, we normally have, for example, this p atomic orbital. It can be divided into two regions. The first one is the bonding region, and the second one is the anti-bonding region. In pi bonding molecular orbital, what happened is that the p orbital, both of the p orbital has the same faces, so they will overlap to give you pi bonding molecular orbital. And then in anti-bonding orbital, there are two faces that are opposite each other. However, because the faces is different, so they cannot overlapping. However, they are forming this pi star antibonding molecular orbital. And you notice that there is a knot in between these two p orbital because they do not overlap. Okay, now let's take a look of the molecular orbital of 1,3-butadiene. So we know that butadiene has 4 carbons. Okay, and now it is 1,3-butadiene. So diene means it has 2 double bonds at carbon number 1 and carbon number 3. Carbon number 1 and carbon number 3. So this is the structure of 1,3-butadiene. Okay, since we have 1, 2, 3, 4 bonds here, so we need to have 4 p orbital. Okay, so this 4p orbital is now divided into bonding region and anti-bonding region. Okay, in bonding region, the faces that overlap must be greater than the number of nodes. So in this case, the lowest level MO is when 4p orbital overlapping at the same sites. So they are all overlapping. And then the second lowest energy molecular orbital has two pairs of overlapping orbitals and then one nodes. In anti-bonding region, we have to minimize the interaction. So in this case, we have one overlapping p orbital, but we have two nodes, which means it is still anti-bonding because we have two nodes greater than one bonding. And then in the highest molecular orbital, in the highest energy level of molecular orbital, we have 4p orbital that are not interacting with each other. So it results in 3 nodes. Okay, for reaction happen thermally, it does not involve electron excitation. So normally the HOMO is around this level. HOMO means highest occupied molecular orbital. Okay, this is occupied molecular orbital. Occupied molecular orbital means there are electrons in the orbital. And then this is the LUMO. LUMO means lowest unoccupied molecular orbital because there is no electron here. So it is considered as LUMO. But in a reaction that involve UV or a reaction that occur photochemically, so when you expose an energy or UV, so one of the electron excite to the anti-bonding region. So the HOMO now goes up, which this is the highest occupied molecular orbital and followed by LUMO at higher energy level. Okay, these are some points that should be noted. Okay, so what is bonding MO? Bonding MO, where a number of bonding interaction is greater than number of nodes. Okay, for anti-bonding MO, number of bonding interaction is fewer than number of nodes. And then ground state. Ground state is a normal electronic state of a molecule, while excited state is the promotion of ground state electron from its HOMO to its LUMO by absorption of light. This excited state usually involve photochemical reaction. Yeah. Okay, in thermal reaction is carried out in its ground state, while photochemical reaction involve reactant in its excited states. Okay, let's take a look at the molecular orbital of 135 hexa triene. Okay, we know that triene, hexa means 6, so we have 1, 2, 3, 4, 5, and 6 carbon. And then we have triene. Triene meaning we have 3 double bond at the position of 1, 3, and 5. So 1, 3, and 5. Okay, in this case, what happened is that we need to have, because it has 1, 2, 3, 4, 5, 6. Okay, triene, it has 6p orbital. So in this part, we have 6p orbital. So in bonding region, we have 6 orbital overlapping. And then we have another pair, which is 3p orbital overlapping, and then another 3 overlapping at the opposite side. So we have 1 node. And then when we have another level is where we produce 3 pairs of overlapping orbital with 2 nodes. And then for the antibonding region, Okay, we produce two bonding interaction with 3 nodes. Okay, so at higher energy level, we produce one bonding interaction with 4 nodes. And at the highest molecular orbital, highest energy level, we have 5 nodes. Okay, please take a look at the ground state. So the HOMO is this orbital because the electron is filled at this highest level. And then the LUMO is this orbital. And then when in excited state, what happens is that one of the electron will jump to the next orbital, and then this is now the new HOMO, and then the next orbital is the new LUMO. Okay, this is an example. Draw the molecular orbital of 2,4-hexadiene, label the HOMO and LUMO in the ground state, and label the HOMO and LUMO in the excited state. When we try to do this, we just follow the example previously, and because it is hexa, means you have 6 carbon, hexadiene, 6 carbon, okay, 6 carbon, but because it is diene, so you have 2,4-diene, 2,4-diene, 1, 2, 3, 4, 5, 6. Okay, so since we have 1, 2, 3, 4, so we have 4p orbital. So this is 4p orbital, where this is the bonding region, this is the anti-bonding region. So in this, the lowest energy level, you have 4p orbital interacting with each other. And then in the next energy level, you have 2 pairs of bonding orbitals with 1 nodes. And then at anti-bonding region, um, you have 2 nodes, where in the middle they are interacting, p orbital. And then at the highest energy level, so you will see there are 3 nodes. Okay, for ground state, the HOMO is this orbital, while this is the LUMO. While in excited state, one of the electron from this HOMO jump to the another energy level, so this now becomes the HOMO, and this antibonding MO becomes the new LUMO. Okay, that's the end of this part. We will continue on the introduction on pericyclic reaction.